Hello everyone. Today I'm going to be coding a binary heap, or at least attempting to. I'm going to be coding it in C++, but I'll be explaining it along the way, so hopefully it'll be mostly easy to follow. And if you don't know what a binary heap is, I have a explanation video which is linked in the description. So first off, let's just read in some numbers. So the way I'm going to do this is I'll read in a bunch of integers and then I will add them into a heap and then do a heap sort and print out the integers sorted. And what this will do will just give a kind of quick sanity check that the heap implementation is correct. So if the numbers, when we insert them into the heap and then we get the minimum of the heap, and then we output that, and then we remove the minimum and we repeat that process, we'll print out all the numbers from smallest to largest. And if the heap is implemented correctly, then it will print it out in sorted order. And if the heap isn't implemented correctly, it may or may not work. So this is not a perfect test, but we'll run it a few times and see how it goes. So first off, let's read in some integers. And let's just print them out again. All right, let's try this. All right, so that seems to work. Now let's implement the binary heap. So we need a backing for the binary heap to store the actual data. I'm going to use a vector of integers. I'll call it nodes. Now, one of the easier ways to implement a binary heap is to start the counting from 1, and that makes it easy to find the parent and the left child and the right child. So I'm adding a -1 sentinel value to just make sure that the nodes vector always contains at least one object. So let's go through the binary heap operations. So one of them is insert. We insert a single integer into the heap. Another one is get the minimum. This one's pretty easy, so let's just implement it now. We just return the root of the tree. Since it's a min heap, this will get the minimum. And now delete min. We can only delete the minimum element in a binary heap, so this will be the implementation of that. Let's start with insert. So what we need to do with insert is we need to insert it on the bottommost row of the left complete binary tree. And when we do this, this may violate the heap property locally, so we need to fix that by bubbling the value up to the tree and keep doing that until the heap property is satisfied or it is at the root of the tree. So let's get the next node index, which is nodes.size. There's one more than the index of the currently last node. And now we'll add the value. Then while the node is not the root node, we need to check the heap properties. So we need to get the parent of the node. All right, let's implement this proper function. Because of the numbering scheme, we can just divide by 2. Now we need to check the heap properties. So if our parent is greater than us, this violates the heap property, so we need to swap these values. And we need to continue bubbling up the tree, so go to the parent. Otherwise, the heap property is satisfied, so we're done. And this will keep going until it gets to the root or till the heap property is satisfied. That should be the implementation of insert. Delete min is a bit trickier, so it's difficult to delete an arbitrary node from a heap because that'll stop it from being a left complete binary tree unless we delete the bottommost rightmost node. but then we're not deleting the min. So what we do is we temporarily violate the heap property by swapping the root of the heap with the bottommost rightmost value. Then we can remove it very easily. Now we just have to fix the heap. This is a bit trickier than the bubble operation. This is called the bubble down operation, and there's a bunch of other names. But now we need to check, before we only had to worry about the parent and whether that was larger than or less than or equal to what we were. But now we have to worry about the left and right child as we're pushing down. So we need to find the smallest node out of the parent and the left child and the right child, and keep in mind that the left child and right child may not exist. So let's assume that the smallest node is all right, we need to start getting a loop. So let's just do a while one until we figure out what the conditions are going to be, and we can just start at the root node. Let's assume that the smallest node is the current node, and then try updating that. So if, let's get the left child, right child, so thanks to the numbering scheme again, we can just multiply by 2 to get the left child and multiply by 2 plus 1 to get the right child. And you notice that when you divide the right child by 2 and the left child by 2, one of them is odd. The right child is odd, so when you divide it, it gets truncated, so this plus 1 goes away. So that's why the mapping, like there's two things mapping to the parent, but the parent maps to two things. All right, so now we need to go through and compute the smallest node value. So we've got to check the left exists and see if it's smaller than the current smallest value. So nodes left is less than nodes. Put this onto the line. Then update smallest node. Same thing with the right. I'll check it exists. And nodes right. And if it's the same value, it doesn't matter whether we go down the left or the right, either is fine. We just want to avoid the situation where we push, for example, the left child up to its parent, but then it ends up being bigger than the right child because the right child was smaller, and then the heap property is broken, so it won't work. Right, so either smallest node is the same as the current node bat, in which case it's already the smallest node out of those 3 nodes and the heap property is satisfied and we're done. So if smallest node equals node, break, because we're done. Otherwise, we want to go down. So node equals smallest node, and we also need to swap these values so we can push it down. Node. Okay, and then when we get to the bottom, both left and right won't exist, so this break will occur, so we won't infinite loop. Alright, so hopefully this works. We'll see if there's any bugs. Alright, we gotta actually call it. Alright, let's create a heap. So binary heap. So insert the value. And then we will do the heap sort. So get the minimum value, then we'll delete the minimum value. And make sure to new line at the end. Right, we didn't include vector. And what's going on here? It's an S, okay. And missed the semicolon. Classic. All right, let's test it out. So let's do a simple case first. Okay, that works. Now let's try some tricky cases. So what if it's size 1? That's kind of an edge case. That works. Size 0. That works. All right, let's try a bigger example. So maybe 8 values, and I'll type in some random values. All right, that's 8 things. That looks like it's in order to me. I typed 432 twice somehow. All right, and let's try negative numbers. All right, that looks like it's in order to me. Everything is in order. And that's the implementation. So to go over this again, we read in the integers, we insert them all into the heap. Heap insertion starts by pushing it onto the backing array, which is adding a value to the bottommost rightmost part of the left complete binary tree. Then we push it up, so until we get to the root, we check its parent, check whether the heap property holds. If it does, we're done. If it doesn't, we need to push up further. And deleting is more complicated. We need to check 3 nodes, find out the smallest one of all of them, and if the node we're currently at is already the smallest, then we're done. The heap property is held. And if there are no children of that node, that's trivially true. Otherwise, we need to push down the path that has the lower value. And that's it. Thanks for watching.